What's up guys, this video is about how a rectifier diode works. A diode is a device that allows current to flow in only one direction, that is from positive to negative. When a diode is reverse connected, current won't pass through. Since diodes and other electrical symbols were designed to follow conventional current, which flows from positive to negative. However, to understand how a diode works, we will use electron flow in our animations, which flows from negative to positive. Conventional current and electron flow are two types of current that differ in direction of flow. While the direction of electron flow is the actual direction of current, conventional current is how current was said to flow before the discovery of electrons in the 70s. And until now, conventional current is the one generally used. A diode in construction consists of two semiconductor materials that have a controlled amount of impurities joined together. One material is called the p-type material and the other is called the n-type material. The impurities added to the two semiconductor materials are to improve their conductivity. Semiconductor materials are the most used materials in electronic engineering. At room temperature, semiconductors are poor conductors of electricity. However, if the temperature of a semiconductor is increased, they conduct. Semiconductors can also be made to conduct well at room temperature by the process of doping, which is the adding of a controlled amount of impurities to a semiconductor material. They are usually doped with atoms of group 3 and group 5. When a semiconductor like silicon is doped with atoms of group 5 such as phosphorus, there is an electron from every group 5 atom that is left without forming a bond. This electron is free and will cause conduction in the doped semiconductor material when connected to a source of voltage. Since silicon atoms have 4 valence electrons or outermost electrons, and group 5 atoms have 5 valence electrons, soon after doping, covalent bonding takes place between silicon and group 5 atoms, in which every group 5 atom will share its outermost electrons, with 4 silicon atoms neighboring it, and is left with an electron without forming a bond. This electron is free and will cause conduction of electricity in the material when the material is connected to a source of voltage. The semiconductor material doped with atoms of group 5 is called the n-type material. In the n-type material, free electrons which are a result of doping are the ones that cause conduction. They are called the majority charge carriers in the n-type material. When silicon is doped with atoms of group 3, such as boron, there is a hole left from every boron atom that is left unoccupied. Atoms of group 3 have 3 valence electrons. After doping, every boron atom will be surrounded by 4 silicon atoms, which have 4 valence electrons. Every boron atom will be short of an electron to complete bonding, and Hose results. This Hose will initiate conduction in the material when the material is connected to a source of voltage. The semiconductor material doped with atoms of group 3 is called the p-type material. A hole is regarded as positive or as a proton. In the p-type material, holes which are a result of doping are the ones that cause conduction. They are called the majority charge carriers in the p-type material. Since free electrons and holes in the n and p-type materials are created by the process of doping, the n and p-type materials have an equal number of electrons and protons. They are neutral. In the p-type and n-type materials shown here, we are only showing the free electrons in the n-type material and holes in the p-type material that are created by the process of doping. When the n-type and p-type materials are joined together, a junction is formed between the two materials. As soon as the junction is formed, free electrons from the n-type material near the junction are attracted by holes near the junction in the p-type material. The attracted free electrons will cross the junction. As electrons cross the junction, the n-type material loses electrons, resulting in a layer of positive charges or holes near the junction in the n-type material. Since the p-type material is neutral, it has an equal number of electrons and protons. The electrons that cross the junction from the n-type material will cause an excess of electrons in the p-type material, resulting in the creation of a layer of negative charges or free electrons near the junction. The opposite charges on the sides of the p-n junction create an electric field that grows in strength as electrons cross the junction, to a level that prevents further movement of electrons from crossing the junction. The two layers of positive and negative charges on the sides of the p-n junction form a depletion region. The potential difference or voltage of the electric field is called the barrier potential. In silicon diodes, the barrier potential is 0.7 volts, and in germanium diodes, it is 0.3 volts. The structure of a diode makes it conduct or allows current to pass through it in only one direction, that is the forward direction. To connect a diode in the forward direction, the negative side of the battery is connected to the n-type material, and the positive is connected to the p-type material. And also for a diode to conduct, the supply voltage must be above or equal to the barrier potential. When a diode is connected in the forward direction, the negative side of the battery repels electrons in the n-type material and forces them to cross the junction. The negative side also provides a continuous supply of electrons. As electrons cross the junction, they give up energy equal to the barrier potential. When electrons cross the junction, they combine with what's in the p-type material and move from wall to wall toward the positive side of the battery, as they are attracted by the positive side of the battery. When a diode is connected in reverse, it does not allow current to pass through it. In reverse connection, the negative side of the battery is connected to the p-type material, and the positive side is connected to the n-type material. In this situation, the positive side of the battery attracts electrons from the n-type material away from the p-n junction, leaving holes, thus widening the depletion region. And at the same time, the negative side of the battery supplies electrons to the p-type material toward the p-n junction, thus further widening the depletion region. This flow of electrons lasts for a short time. As the depletion region widens, the electric field between the opposite charges increases in strength until the potential difference across the depletion region equals the supply voltage. When the reverse voltage across a diode is increased to the reverse breakdown voltage, the diode breaks, resulting in the flow of high reverse current. The value of reverse voltage at which the diode breaks is called the reverse breakdown voltage. A rectifier diode should be operated below its breakdown voltage. The characteristic of a diode to conduct in one direction makes it useful in various applications, such as rectification and polarity protection. In polarity protection, a diode is used to prevent current from flowing when the voltage source is wrongly connected to the load. For example, if the battery is connected vice versa, with the positive side is connected to the neutral and the negative side is connected to the live conductor, the diode won't allow current to flow. But if the battery is correctly connected, it will allow current to flow. Okay guys, that is it for this video. I hope you find it helpful. Catch you in the next videos.